All right, let's look at a new problem. Let's find the half-life of a compound that decays at a daily rate of 1.25%. So, as you can see, this is a half-life problem, and we haven't done quite as many of those. Just to make it clear what kind of half-life problem this is, we are looking for the half-life, right? And we are given a rate. So we're going to see other half-life problems where we are given the half-life and we have to do something with that. And other problems where we're given points instead of rates. But in this case, we have no points, we have a rate. So our model, since we don't really have an initial amount, what can we really say? Well, let's assume that we have 1 unit, and our factor is going to be 1 minus 0.0125, and then we're raising this to the t. So I hope you understand where this came from. We converted this to its decimal form and made it negative because it's a decay rate. So this is our model, and then we want to know how long it takes for this to get to 1/2 because we started off with 1. So we'll let y2 be 1/2. All right, so now I'm going to enter that in the calculator. Okay, so I've brought my calculator up and entered the function. Here it is. And then for y2, I've got 0.5, and I want to do my intersection of this. Let's go to the table and see if we're anywhere near the right spot. Actually, it's not too bad. I just happen to be in this range, and that's not too far off of 0.5, so you can see here we are approaching it. So probably if I go to like 50, that would be okay. Maybe. We might need to go even further than that, actually. Yeah, let's go to 75. Now I'm doing calc or zoom fit, and then I'll do calc intersect. Okay. And we find our intersection point is 55.10. So that's our daily decay rate. All right, a little more review. This is just about the formula for the exponential function passing through 2 points. Now, honestly, this notation, I'm not actually going to use this notation very much, so I don't want to be confusing. But what I would prefer to use is this notation. Oops, I made a mistake, I'm sorry. Okay. Same difference, I'm not using the subscript notation. And then down here we have the formula for the growth rate. That's a multiplication right there, by the way. The formula for the growth rate, which is essentially just a portion of this. So in my notation, that would be a(n) over a0 to the 1 over n, and then we subtract 1 from all of that. Now, having said all of this, I want to point out that it's probably better and faster in these sorts of problems to use exponential regression than to use these formulas. So we can almost, whenever you're given 2 points, you pretty much can always use exponential regression. Okay, so having said all that, let's find a problem where we do some of this. And that's what this slide is talking about, is using exponential regression. Okay, so here we go. Here's an example. Find the decay rate of a compound with a half-life of 37.6 hours. So notice here that the half-life is given. When you have a half-life given problem, generally I'm going to use exponential regression for that. And here's how I'm going to use it, is I'm going to set it up so that in column L1 I have my time. So I start at time 0, and then I go to 37.6 hours, and that's my half-life. And then for L2, I'll put in my amounts. Now I don't really have an amount, so I'm going to assume that I start off with 1 unit and then I go to 1/2, and then I'll do exponential regression with this data. I've got my calculator pulled up, and I'm entering my numbers. And then we will exit, go to stat calc, scroll down to expreg, which is number 10 or 0, L1, L2, save it as y1, and there's our function. So 1 times 0.98 to the x. Or to the t, I suppose. So here's our answer. Well, somewhere. Here it is. Okay, now all these intervening slides, what was all that about? Let me just kind of go back and quickly address that. Actually, you know what? I just realized that I didn't actually find the answer. I found the model. The question actually said to find the rate, so I'm sorry, I kind of got ahead of myself. We found the model, but we actually want the rate. So how do we actually get the rate from this? So if the model is a of t equals 1 times 0.9817 to the t, then what's the rate? Okay, so let me bring that back up. My calculator, I mean. There's my full b value, my full factor. What I need to do is subtract this number from 1. So I'm going to do 1 minus, and I want to call up that number. And I could type it in, but I'm also kind of lazy. So let me just do this. I'll go to vars, statistics, equation, b, hit enter, and there I've got my difference. So 1.83. Okay. So 1.83% is my decay rate, and that's what we're talking about down here. This has found the actual growth rate, and that's why it's saying negative, but then the decay rate is positive. Okay. Okay. Now, if you use the 2-point exponential form, you can certainly still find the growth rate with that. It's a bit messier. And this slide talks about how to do that. You actually, let's go back a bit. Okay, so if you wanted to use the 2-point exponential form to find the growth rate, what you have here is the new over old. New over old, that's your ratio. And then so that's our ratio, which means it's our of successive values, and therefore that's our factor. And so we're going to raise our factor. We're basically converting this to the using the doubling time. So we raise it to the 1 over 37.6, which that's our doubling time, right? Subtract 1, that gives you your decay rate. So it's the same thing. We're converting a time unit. To its rate form. Okay, but really I think that the exponential regression version is much simpler, so I would recommend doing that. Okay, and that's what we did here. All right, so let's look at another example. This is a population decay model. During the second half of the 20th century, the population of Washington, D.C. decreased exponentially. So our population on July 1st, 1950 was 802.2 thousand, and by July 1st, 2000, the population had dropped to 572.1. Find a model for the population as a function of the number of years after July 1st, 1950. So this is we're given data, so this is a point-driven model. We have no rate, we have data. I would use exponential regression here. And I'm going to set that up in the calculator. So my calculator's initial time is times 0, and then we go 50 years forward to 2000. Our initial population is 802.2 thousand. Whoops. And then we fall to 572.1. And now we're going to do exponential regression. And there's our model, 802.2 with this decay factor. So I have my model now. Keep referencing the calculator because I forgot it. 99, oops, that was actually 9933, I'm sorry. 9933. To get my decay rate, I need to go back to the calculator and use the b value and subtract that from 1. So I'll do 1 minus, this is the way I like to do it, is I call it the b, the full, oops, I messed up though. VARS statistics equation b, and multiplying by 100 will give me my percent form. So it's 0.674%. And then finally, to get the 2010 population, we just evaluate the model in the appropriate input, which would be 60, because we started in the year 1950 and we're talking about 2010. By the way, this is an extrapolation because it's outside of the data set, 534.70. So this is an extrapolation, which means it's probably wrong, but maybe not. Okay. And as you can see, this is the method I use, exponential regression. Okay. And as I said, the actual 2010 population was 601,000, so it was wrong. That we do have significant model error. Oops, sorry. And here I've computed this model error and this percent error. So basically, the decreasing exponential model is no longer valid. It's valid for over a period of time, but not into the present. All right.